Okay, looking here at example 7, we have simplifying derivatives. The next three examples, 7, 8, and 9, illustrate some techniques for simplifying the raw derivatives of functions involving products, quotients, and composites. So here, we're going to take this derivative, and just by looking here at example 7, we have two terms. This is going to be a product rule scenario. And the big part is going to come after we find this raw derivative, simplifying it, making it look a little prettier. And in example 7, we're going to do a little technique called factoring out the least powers. And you'll see what I'm talking about as we work through the problem. So here's our function f of x. Again, it is two distinct functions multiplied together, so this will be product rule. The first function, x squared, that's a nice easy derivative, 2x. This here, we have a radical, so I'm going to rewrite it as a half power, that 1 minus x squared to the half power. And when we take the derivative of that, it's going to be 1/2 times our same quantity, 1 minus x squared. But now to 1 power lower, half minus 1 is -1/2. And then we take our inner function's derivative. This is our inner function, 1 minus x squared. That derivative is -2x. And to clean this up even a little bit more, we can do the 1/2 times the -2. So that's going to be -x times our quantity. Oops, what am I doing? 1 minus x squared to the -1/2 power. So let me clean this here and move this up. So we have our two functions and our two functions derivatives. So we're ready for the product rule. F prime of x equals, well, that's the first times the derivative of the second. So we're going to sort of multiply on this diagonal. Let's see here. So we're going to have 2x. No, first times the derivative of the second. Yeah, first x squared times the derivative of the second. So x squared, and then the derivative of this is we multiply by another -x, and then our quantity to the -1/2 power. So first times the derivative of the second, plus second times the derivative of the first, and that's going to be our 2x. And let's rewrite that radical as a rational exponent, 1 minus x squared to the half. So there's our derivative f prime, and we just did that with the product rule again, and it's a little messy looking. So the idea here behind example 7 is we're going to simplify this by factoring something out. And what we're going to factor out is the least power, and that usually involves, we have a quantity in parentheses. Here I'll underline in red, we have our quantity to the -1/2. We have the same quantity to the +1/2. So we're going to factor those out, and anything else that we can. So let me put here in red a couple brackets, and let's figure what we can pull out of each term. The first thing I see is an x. We have an x squared here. We have a 2x here. So we can factor out an x. When we factor x out of this first term, let's see, here we have a -x in parentheses. We factor that x out. This will become a -1 times our x will be or x squared will be a -x squared. And then we're going to have a plus here. We factored out this x, so we're going to have a 2 left. Well, what else can we factor out? We have the same quantity, but two different exponents. And that doesn't mean we can't factor part of that out. And we're going to factor out the least of those powers. So we have our quantity, 1 minus x squared. Which of these is the least of the powers? Well, the -1/2, of course, is the smaller of the two. So that's what we're going to factor out. So we factored out this quantity to the -1/2. This is completely factored out, so we're just left here with this -x squared. So I guess that means I can move this over a little bit. Plus 2, we factored out this x. Now, here's the tricky part. We factored out this quantity to the -1/2 power. And here, when we factored it out of this, this already had a power of 1/2. Well, here's a way to think about it. We have our quantity. When we multiply like bases, we add exponents. So here we have this quantity to the -1/2 power. If we were to multiply by this one here, it would have a power. And when we add those powers together, they're going to equal +1/2. Well, -1/2 plus what is +1/2? That has to be first power. And look at that. Now that it's the first power, we can sort of drop the parentheses after we distribute that 2. So let's do that right now. And we have our bracket. We're going to distribute that 2. So that'll be a 2 minus 2x squared. And we're getting close. Just one more thing we can do inside those brackets. We have some terms we can collect up and combine. So here, let's just look in the brackets. Negative x squared minus 2x squared is negative 3x squared, and we have a 2. So let's write that as 2 minus 3x squared. And then we have this stuff out front. Well, this x has a power of the first, so that's going to stay here in the top, in the numerator. But this negative 1/2 exponent is going to drop this term down to the denominator. And that'll be 1 minus x squared to the 1/2 power now. And there's our final, complete and simplified derivative. And let me get back here. F prime of x is equal to this. So let's see what's happening here in example 8. Simplifying the derivative of a quotient. So we are going to probably be using the quotient rule here. And then when we get our raw derivative, we're going to have to simplify something. So let's see here. Let me just rewrite the function. Our numerator is x. Our denominator is that quantity, x squared plus 4. And let's rewrite that to the 1/3 power. So now we need our derivatives. Our numerator's derivative, nice easy 1. Our denominator's derivative. We're going to need the chain rule here. Bring the exponent down front, 1/3 times our quantity, x squared plus 4 to 1 power lower. 1/3 minus 1 is negative 2/3. And then the chain rule says we tack on the inner function's derivative. Here that inner function would be x squared plus 4. Its derivative is 2x. And then to combine this a little bit more, the 1/3 times the 2x, we could make that a 2/3 x times our quantity x squared plus 4 to the negative 2/3 power. So here is our denominator's derivative. We have our high and low function, we have our d high, and we have our d low functions. So we're ready for the quotient rule, f prime of x. And we start off our quotient in the numerator, low d high. So here is our low function, and I'm going to rewrite that as a rational exponent, of course, x squared plus 4 to the 3rd. So low d high, the derivative of the upper is just a nice easy 1, minus low d high minus high d low. So x times the derivative of the denominator, and that was our 2/3 x times our quantity x squared plus 4 to the negative 2/3 power. And then we have our overall denominator, low, and that would be our quantity x squared plus 4 to the 1/3 power, and we square that, low, so that to the 1/3 times itself, that quantity squared, we can just rewrite this exponent as 2/3. Oops. So we have that to the 2/3. Okay, let's see what this looks like. The numerator is kind of like the last example when we use the product rule. So we might be able to factor something out there and then see if it cancels maybe with something in the denominator at some point. So let's see here. Do our divider line in that numerator. Well, it doesn't look like we can factor. Here's an x and another x, but we can't factor an x out of this side. So it looks like we just will be able to factor out that quantity, x squared plus 4. And then we're going to have some stuff here in the brackets left. And what exponent should we factor out? We had a 1/3 and a negative 2/3. So let's factor out the negative 2/3. That's the least of them. So when we would think about foiling this out or distributing, we were going to combine our exponents. Negative 2/3 plus what is 1/3? Well, that's going to be first power. That works out nice. So at some point we can just drop those parentheses. Minus, here we have x times 2/3 x, so that's going to be 2/3 x squared. And then we factored out this negative 2/3 exponent to our quantity, and here it is. We factored that completely out. So here we're just left with that negative 2/3 x squared. And then we don't forget, we still have our denominator, x squared plus 4 to the 2/3. Okay, can we combine anything else? Don't let me forget my notation. This is our derivative f prime of x. Let's look in that numerator. Is there anything else we can factor out of there? It's not completely necessary, but it does make it easier to work with. We can factor out, get our fractions outside of this quantity. Here in front of this first quantity, there is a coefficient there. There's a 1, or we could think about that as 3/3. And here we have a 2/3. Well, to get rid of fractions, we can factor out a 1/3. So here in our numerator, we'll factor out with our quantity to the negative 2/3 power a 1/3. Now, what does that leave us in the parentheses? Well, we had a 3/3 and we factored out a 1/3. 1/3 times what is 3/3? Well, that's got to be a 3. And then we have our x squared plus 4. And then we factored out, we have our minus 2/3. We factored out a 1/3. 1/3 times what is 2/3? Well, that's just a 2x squared. And our denominator is still low. X squared plus 4 quantity to 2/3. Now we just have a little more simplification there in those brackets. Still, we can distribute the 3 and combine our like terms. So outside those brackets, we still have our 1/3 x squared plus 4 quantity to negative 2/3. And let's see here. We're going to distribute this 3, so this will be a 3x squared plus 12. Then we'll have 3x squared minus 2x squared. Well, that's just x squared plus 12. And then we have our denominator, x squared plus 4. And I'm going to write that right underneath, because look at that. In the numerator, we have an x squared plus 4 quantity. Denominator, an x squared plus 4 quantity. And this is still our derivative, f prime of x. So almost home. A little more simplification. Let's see how we can make this look prettier. F prime of x. We're going to have our fraction. This 1/3 in the numerator, we can sort of drag that down front and have it as a 1/3. So the 1 would still be in the numerator, and the 3 would now be in the denominator. The numerator definitely stuck up there is x squared plus 12. Now these, x squared plus 4 over x squared plus 4 with these exponents. What happens if we have x to the 7th over x squared? Well, we keep the same base x and we subtract the exponents top to bottom. 7 minus 2 would be 5. We'll do the same scenario here. Our quantity will still be x squared plus 4. And the new overall exponent in the denominator is negative 2/3 minus 2/3. So that'll be 4/3. Or you could think about it this way. We could take this x squared plus 4 to this negative exponent in the top and move it down, and have another x squared plus 4 to the 2/3. And then since we're multiplying like bases, we would add the exponents. 2/3 and 2/3 is 4/3. So there's our derivative. The idea behind it, applying the quotient rule wasn't the worst part. After that, when we just had to use some algebra, factoring stuff out, that's where you can run into the trouble. Okay, one more of these. Example 9, simplifying the derivative of a power. So here, when we first look at this function, I see we have a quotient in the parentheses. So probably in here, we're going to have to use the quotient rule. And then I also notice that we have a set of parentheses raised to a power. And that is a dead giveaway for the chain rule. So let's start applying that chain rule. Y prime equals, of course, we're just going to move that exponent down front. 2 times this same quantity, 3x minus 1 over x squared plus 3, to 1 power lower. That was squared. Now it's first power, so we don't have to write it in. And then I'm going to write the rest of it this way. The chain rule says we need the derivative of this inner function. So we need to take d dx, the derivative with respect to x of what's going on in here. Oops. So this is where we're going to need the quotient rule. Our high derivative, our high function is 3x minus 1. D high is just going to be 3. Our low function, x squared plus 3. D low is going to be 2x. So this won't be too bad of a quotient rule. So continue on with y prime. We have 2 times our quantity. Oops, that's ugly 3. And the derivative here, quotient rule. Low d high, so 3 times that denominator. 3 times the quantity x squared plus 3. So low d high minus high d low, 2x times our numerator, all over low low, this denominator quantity squared. Alright, we're getting somewhere. And actually there's not too much to do after this. Just a little algebra. And the beginning of this is going to remain the same for now. 2 times our quantity here. In this numerator, distribute the 3. So we're going to have 3x squared plus 9. And then a minus 6x squared plus 2x all over that same denominator, x squared plus 3, quantity squared. Okay, a little more work, just combining what we have in here. And we're going to break this up into, the numerator and denominator separately. You'll see why in just a minute. We're going to have that 2, and then we'll have this quantity times what's going on in here. So we have our 3x minus 1 times what we simplify this down to be, and then look at the denominator, x squared plus 3 times the quantity x squared plus 3 squared. That gives us a nice denominator of x squared plus 3 to the third. And what do we have in here? Let's see, we got a 3x squared and a negative 6x squared, so that's a minus 3x squared plus 2x plus 9. And that had a lot going on into it. Kind of a complicated problem with the chain rule and the quotient rule built in. But again, what's really going to trip up a lot of people is just some of that algebra. Okay, I guess in this video we have time to squeeze in the transcendental functions with the chain rule. And these aren't bad at all. We have, remember, if we had sine of x, the derivative of that would just be cos of x. And that was because, this x was a simple 1x to the first power. But what if we have something else going on, like the sine of x squared? So we're going to think about this inner of the composite function as a u. This would be the sine of u. So we'll take that derivative and then we'll tack on times the derivative of that inner function u prime. So if we have the derivative of sine of u, or we're taking the derivative of that, its derivative is the cos of u, the cosine of the same value, whatever that is, times u prime. The derivative of cos was negative sine. Well, now it's negative sine of u times u prime, that inner function's derivative. And it's all the same for tan and cotan, secant and cosecant. Just how we learned to do it before when it was just a simple x, and then we tack on that inner function's derivative. And it also works with the exponential function. The derivative of e to the x is e to the x. But now what if we have something going on up there like e to the 7x squared? Well, the derivative of e to the 7x squared is e to the 7x squared times this upper function's derivative. What is 7x squared's derivative? 14x. Let's try a few examples. So example 10, y equals the sine of 2x. And all the time when I was in high school and college, sometimes I would parenthesize that off to make me really focus on that as an inner function u that we will have to derive. So the derivative y prime is derivative of sine is cosine of the exact same inner function 2x, and then we got to tack on the inner function's derivative. The derivative of 2x is 2, and then we can pretty that up by writing it as 2 cos of 2x. Here's basically sort of the same thing. Now it's just an x minus 1 instead of just a 2x. But finding the derivative is relatively simple. The derivative of cosine is negative sine of that exact same quantity, x minus 1, and then times the inner function's derivative. What's the derivative of x minus 1? Just plain old 1. The last one, c, y equals e to the 3x. So that derivative is the same thing, e to the 3x, times that upper or inner function's derivative. 3. And then we can just write that as 3e to the 3x. So here in example 11, it says parentheses and trig functions. So we're going to focus in on what parentheses do, to take in these derivatives. Here in the first one, letter A, y equals the cos of 3x squared. And that 3x squared is a quantity, so we can sort of parenthesize it off again to make it sort of pop out, and we realize that that's an inner function of a composite, and we will need to take its derivative. So let's see here, the derivative of cosine is, this is going to be y prime, negative sine of the exact same quantity, 3x squared, times that inner function's derivative. The derivative of 3x squared is 6x. And then, we'll put that 6x out front of the negative sign. Negative 6x times the sine of 3x squared. Now, the parentheses for part B have moved a little bit. Here the parentheses were around the 3x squared. Now it's the cos of 3 in parentheses times x squared. Now, there's a couple ways to approach the problem. You could think, okay, it's a product rule. We have the cos of 3 times a 2x. Well, the cos of 3, we can punch that in the calculator, get a decimal. The derivative of any constant is 0. And the derivative of x squared would be 2x. And we could go about it that way. First times the derivative of second plus second times the derivative of the first. And actually, let's just finish it off. We have our first times the derivative of the second. That's going to be the cos of 3 times 2x. Plus, the other way is going to be 0 times x squared, which would just be 0. So we have the cos of 3 times 2x. And we got that with the product rule. A different way to think about this is, remember, the cos of 3 is just a number. What if this was 2x squared? What would the derivative be? Bring the 2 down, multiply by the 2, it would be 4x. We're sort of doing the same thing here. We could bring this 2 out in front here, so it's going to be 2 times the cos of 3 times x to the first power, or we could rewrite it as 2x cos of 3, just like we found with the product rule. Another variation on the parentheses. Here the 3x squared was totally in the parentheses, 3x squared. Now we have the 3x in parentheses, quantity squared. And we can simplify that a little bit by, working this out. 3x squared, 3x times 3x is 9x squared. Now this will be, a lot like the first example then. The derivative of cosine is negative sine of the exact same quantity, 9x squared, times that inner function's derivative, 18x. And then rewrite it, we'll put the negative out front, negative 18x times the sine of 9x squared. All right, letter D. Another movement of the parentheses, so to speak. Here it's cos squared of x. It's not the x that's squared, it is the cosine function itself. And remember, another way to write this, we can parenthesize that off and move that to outside. Cos of x quantity squared. Now it's a little easier to see that this is just going to be a little chain rule. Bring the 2 down front. 2 times the cos of x, now to the first power, so we don't have to write it, times our inner function's derivative. Here's our inner function cosine. Derivative of cosine is negative sine x. And I guess we can just pull this negative out front with the 2. Negative 2 times sine x cos x, or you could write cos x sine x. It doesn't matter. The last one here, now it is the square root of the cosine function, or you can rewrite that with rational exponent, cos of x to the 1/2 power. And it'll just be, again, another chain rule. Bring the 1/2 down front. We're going to have the cos of x to 1 power lower. 1/2 minus 1 is negative 1/2. And then our inner function again is cosine. That derivative is negative sine x. And let's see, what can we do here to simplify this a little bit? We have that negative exponent. Let's drop that to the bottom. We have our fraction. We have this 1/2. We can split that up. 1 up top, 2 in the bottom. The negative sine x is going to stay up top, negative sine x. The denominator will now have the cos of x to the 1/2 in it. Cos x to the 1/2 power. And there we go. I guess that's as simplified as we can make it. So again, pay very particular attention to those parentheses, where they are and what they mean. Example 12, I think this will be the last one for this video. Repeated application of the chain rule. Sometimes you're working the chain rule once and it pops up and you sort of have to do it again. A chain rule within a chain rule. So here we're starting out with f of t, and that's sine to the third, sine cubed of 4t. And again, we can rewrite that as the sine of 4t all to the third power. So let's start with the derivative. F prime of t. Bring the 3 down front. 3 times our quantity unchanged, sine of 4t, now to 1 power lower, quantity squared. And we have our inner function that we need to take the derivative of. We need the derivative of sine of 4t. Well, the derivative of sine is cosine of that same quantity, 4t, times the inner function's derivative. Now our inner function is just the 4t, and that derivative is 4. So let's see how we can clean this up a little bit. We have a 3 and a 4. We can multiply those and get a 12. And then we have our sine of 4t all squared. We could rewrite that now as sine squared of 4t. And then our cosine of 4t. And there's our final derivative, f prime of t.